Okay, so hopefully this goes well. If this phone behaves, then we can get started with the webinar that is going to literally start in like 3 minutes. I really do hope that it's going to work. This phone better not pull any crap because, I mean, we're going to be over there, right there. That's where we're going to be. Gotta get set up for this webinar. That's what we're going to be going ahead and going to be doing. Pull the chair out. Go over here. Yep, this is what we are going to be doing today. We're going to be doing the webinar. I'm not going to really be paying attention to the stream, so if something happens to stuff like that. Let's go ahead and join this webinar here. There it is. Oh, don't hear anything yet, so hopefully it'll take a few minutes, but it is. We are now ready pretty much for this. If this phone behaves, hopefully this will go well. So here we go. We're going to pretty much be here. There it goes. I see something, but I don't hear anything. So hold on, let me back out of here and go back to my email here, see if I can do something about the sound. Like literally my thing is on full volume and I'm not hearing anything. Unless if I am supposed to...
The webinar will begin shortly.
Oh.
Please remain on the line.
Ah, okay. Okay, thank you. But hopefully there is sound. So anyway, the only way we're going to be both be able to see this webinar is... That's cool. Okay, nice. So here we're going to go ahead and start. I'm pretty much not going to really be paying attention to this chat. Unfortunately, I can't really do that. So we're going to go ahead and... So we can do...
Will begin shortly. Please remain on the line.
I know you are. Let's see. What is the best way to do this? Obviously, we don't want my finger in the way. If I can ever get this thing to stay up, that would be very nice. So, pretty much this is the only really way we're going to be able to watch this. Jesus. Doesn't want to stay. Stay. So pretty much, I will be watching the webinar until it's dinner time for me, and then I'm pretty much gone for dinner.
The webinar will begin shortly. Please remain on the line.
I get it. Okay, I get it. Good. Alrighty. Hopefully they will be getting started shortly, but again, if any crap goes on, I don't really have anything else to really do it with. Pretty much that's the best view we're probably going to be able to get. Unless if I turn down the thing a little bit, but I think I might have to close the curtain and put the light on because might not be able to see stuff very well. So there is basically the stream here.
The webinar will begin shortly. Please remain on the line.
I get it. They must be a little bit behind on schedule, so that's okay. We'll wait, and then, yeah, I think what might happen... Let me go and shut the blinds. That might help with the lighting. Plus, the sun is about to come in and hit the area that we are in. So, we're going to prevent that, and basically... just shut this stuff for now until it gets later at night. There we go. I think we're getting some stuff here. But in the meantime, let's see what we got going on here.
The webinar will begin shortly. Please remain on the line.
There we go. So anyway, okay.
The broadcast is now starting. All attendees are in listen-only mode.
There you go.
Hey, good evening, everyone, and thanks for joining.
All right, guys, we're gonna listen to this.
My name is Michael. I'm from the National Weather Service here. Introduce yourselves.
Yeah, I'm Steve. Steve Travis. I'm a meteorologist here, forecaster at the Weather Service here. So,
Jesus Christ! Just
I use the radar a lot
stay.
operationally, as does Mike. And I'm really looking forward to doing this training this evening.
And then for the radar, and also work on the weather radio stations. I've been here at the office for
God damn. Come on. Jesus Christ. Jesus. Alright, hold on. I gotta apparently find another stand somewhere.
Before we really get started with the content, we have a question section available in the slide panel for
What
this
hell am I
webinar.
supposed to use for stand?
In the questions drop down, you can click on that.
Apparently the Christmas tree's not enough.
So we can usually keep up with those in real time and answer them to the best of our ability.
Going to have to move the
So
tree
that's
over
available
here.
in there. And then also we have some webinar materials in the form of PDFs. They are available in
Move
the
that right there, and we'll see if the 300
there.
will help with it.
That includes a copy of these slides that we're presenting tonight, so you can keep that for your reference, as well as
Dadgummit.
other things such as ham radio network and all the other stuff that you might need as a spotter. So that is also available there. Next thing I'll talk about, I think many of you already know who we are, but just a very brief introduction. The National Weather Service and State College is a
Jesus Christ, how am I supposed to flip and stand this up?
in the United States.
Yep, 300's not gonna help, so we're gonna have to use a damn tree.
6 electronic technicians and IT support, a hydrologist, science operations officer, some other managers, and
Gee,
we are
how the heck is it taking so long for this to freaking set up?
providing
If
forecasting
only
warnings, as well as
this
maintaining
dang phone
Doppler radar
stood up when I wanted it
system
to.
and other observation systems. So, as you heard tonight, we'll have
There, that's the best
Phil
view you're
Feather
probably
with
gonna
us
get,
as
so
well.
enjoy.
He's one of our electronic technicians, and for those of you who are wondering what's going to be different about this presentation versus others we've given in years past,
Alright, I'm not gonna be paying
some of
attention to
that
the
Phil
chat,
will be
so
presenting about the nuts and bolts of the radar. I think is going to be some of that exciting new content. And then how to find us online, just real briefly, there's all our social media handles. And this map on the left shows you what part of Pennsylvania we cover, this yellow portion here, about the central one half of the state of Pennsylvania.
dang it.
Throughout this webinar, we will have a few poll questions as well that we will launch and you can answer. So this is the first one here.
Uh-oh.
How did you hear about this training session? I'm going to go ahead and launch
We're
the poll.
gonna have to launch the
It takes just a
poll.
sec to pop up on your screen. And then
Alright,
please
I got
respond. And,
a poll
give you a few
from
seconds for
this.
that. And then I'll close the poll and we can read it off. Looks like about 75% of the audience has voted so far. A few more answers are trickling in. Okay. All right, there's our results. Looks like the majority found out from our website and from social media. So again, regardless of how you found out, we are definitely glad that you're here tonight. And thanks for being with us. This webinar will take about 2 hours, maybe a little bit more as far as how long the presentation will take. We will have an intermission at some point near the middle of that, so about an hour from now. And we will try to keep it a little bit shorter than last year's version of this course, which went on about 2.5 hours, 2 hours and 45 minutes, or in depth in the question section.
Excuse
For
me.
those who are really interested. Another poll question that we'll launch.
Dude, you got offline now too? Jesus Christ, why the hell does everything have to go wrong in here? Why does everything have to go in here? Just why? Yeah, I'm not gonna be surprised if you flippin' logged off. Either that or you want to reset. That's what you want to do. Not be surprised if you...
Everybody knows that. So stands for radio detection and ranging,
Well,
radar. And essentially what the radar does is...
Gotta reset it again. Alright, let's go ahead and reset it. Why the heck? Why is everything going wrong tonight? I don't get it. I don't like it.
Hailstones, or even some non-meteorological objects like insects or bats and birds. Whenever it hits, most things will absorb some of that energy and then re-radiate it back to the radar and the radar listens as well as transmitting the energy. It listens for energy bouncing back, and based on the time that it takes for that energy to go out and come back, that's where the ranging comes in, and it allows the radar to place exactly is located.
Look at my flipping battery at first of all.
Radar means, and this is what I was talking about as far as the radar shooting out some electromagnetic energy and it hitting an object. In this case, it's a duck in the atmosphere. That object absorbs some of that energy and then returns it back to the radar, and the radar is in a listen mode. And then so I will turn it over to Phil Feather now to talk more about the hardware of the radar and how he and the staff here maintain that hardware.
Hi, our radar is located in Black Shannon State Park, so we don't have the radar on site like with the office, most offices do.
Of course you do.
So it's about a half hour to get out there. So anytime it goes down, we've got to come to the office if we're not working at the time and head out there and troubleshoot it. It's kind of a dicey haul sometimes with the ice, but we can get up there almost all the time. I can only think of one time really that we had to turn around and come back. But that's it for this slide there. On the left is the transmitter cabinet where the transmitter tube is. Coming in, and it ends up producing a power of about 650,000 watts. Tube can generate 1 million watts, but we only run it at about that power level. Because of, the tube is kept cool, and so it's a very stable temperature all the time. So it's a very stable signal being outputted. The tube is cooled by airflow. You can see the air hoses coming into the top and into the bottom area there. On the bottom, there's a metal tank that holds 26 gallons of oil, and it is circulated through a radiator on the left side in that closed cabinet. And it circulates around in there to keep the tube a constant temperature. That's it. Now here you can see on the left the air cooling ducts going into the tube, and you can see that black tube, I guess, in the background in between the two air ducts going in. When energy is at a very high frequency, this is 2.8 gigahertz instead of 60 hertz like the power in your house. It doesn't travel down the wire very well. It would just travel on the skin of the wire.
Why the fuck are we having so many
the way
freaking problems
that they
tonight?
get the power up to the dome is that that pipe in the background is a rectangular pipe, and it is hollow, and it is 1/4 by 1/2 of the wavelength of the frequency that we're at, and that's the most efficient way for the power to get up to the tower. On the
So
right,
now I have to hold it this entire flipping time.
pressurization unit, and it keeps it overpressurized so dirt can't get in and water can't get in, because if it did. On the left, you can see where, after it's in that black section of the waveguide, you can see where it travels out of the building. There is a dummy load, and if we don't want to transmit out while we're doing maintenance, we send the power into that so we can align it that way.
Is anything ever going to fucking work?
The pipe has to be able to turn, and if it did, it would just twist off, along with the power goes up there for all the other electronics. So over here on the right, the kind of bended waveguide section you see there can actually rotate. It's called rotary joint, and it can transfer the power even though it's two rectangle pieces. They have designed a way that it can rotate and still
Jesus.
very effectively. Kind of a cylindrical assembly above it is where the electrical power for all the electronics comes in, your 120 and 240 volts. Inside of that are metal platters, approximately about 10 of them, and then the wires come into that, and then they have little metal fingers that rest on these cylinders, and so it can rotate, and the fingers transfer the power to the electronics. We have to clean those off quarterly because they'll build up dust on them, and it can cause erroneous signal losses and errors. This is looking at the dish up there. It barely fits in there. The radome is only 3.5 feet on each side of it, clearance. Sometimes have to build to work on the electronics on it. And you have to make sure everything is laid down properly so that it doesn't and cause serious damage to the dish or to the radome. We've got a couple of heaters here that you can see, the square boxes. They're installed so ice doesn't build up on it. And we had a big ice shell came off and it damaged some ventilation louvers down on the ground. And so we added another.
Check the replay just to make sure that it's facing at least the good way that I need it to be facing. This dang thing decides to do what the heck I want it to do. Yep, okay. Check the replay.
And you have to make sure everything is laid down properly.
Yep.
So that it doesn't
Okay.
and cause interference.
Looks like it's good, so gotta get back onto my email here.
Great. We can run all kinds of different tests on it. And we have to load software into this occasionally to make new improvements on its coverage and detail of coverage. On the right is the VSAT satellite. We have one of these on the office also, and it will automatically switch over to this. It bounces off of satellite and then comes right to the office, and back and forth we can communicate with that.
All right. Thanks very much, Phil. Really appreciate the photos that you took and the good detailed explanations that you have for all the radar. I mean, to me, it's still fascinating as a forecaster. I think we take so much for granted as far as all the work that's gone into it and all the technology there to keep these radars up running all the time. It's pretty remarkable. So thanks again, and hopefully the audience learned a few things there. And again, if there's any questions, feel free to type them into the chat. So I will continue with some details about the electromagnetic radiation that is sent out of the radar. So I think it's pretty fascinating. There's about 1,300 transmit and listen cycles per second. The transit time for each pulse of energy that comes out of the radar is very, very, very short. It's this red number here, 0.0000157 seconds. So just a minuscule amount of time that it just sends out this pulse of energy, and then it spends this amount of time, which is for that energy to bounce back off of different scatterers out there in the atmosphere. Radar is only transmitting energy for a total of 7 seconds. They're very split up with these intervals, but if you add it all together, it's only transmitting for 7 seconds, and then spends the other 59 minutes and 53 seconds in 1 hour listening. So that's pretty remarkable to think about how much of that time in an hour the radar is actually silent, not transmitting data, but actually listening for returns. Kind of a fun fact there. And as far as the wavelength that gets transmitted from the Weather Service radars, the Weather Service uses S-band. Length is about 10 centimeters. That's about the same as a microwave. This is the best balance of all wavelengths for our national radar network because we need to not only be sensitive enough to detect the hydrometeors, but also we need to have that wavelength not attenuate or not get weaker as it hits things in the atmosphere. We wouldn't want it to just be able to penetrate through the back of a thunderstorm and see more weather behind it. So that's why we need to use the S-band. There are other band, which is a smaller wavelength of 4 to 8 centimeters. This is generally a cheaper and smaller dish, less power, but it does get more easily attenuated. And then, which is used a lot in research, if you see those Doppler on wheels trucks, a lot of those are X-band. Those are the shorter wavelength, even compared to C-band. They're 2.5 to 4 centimeters. So they're very sensitive, and they can see really high resolution structures and pick up very small amounts of precision and tell differences in a lot more higher resolution, but they also attenuate quite a bit, so they won't be able to see as far versus S-band. Okay, so a little bit more about how we interpret radar. So when you look at the spatial interpretation of a radar image, like this one here, for example, the radar is located here in the middle, this little black hole. That's where the radar is. And then it's transmitting energy all around and then it adds up all those beams as one revolution or one scan. And the thing to note about it is that as energy is moving away from the radar, it's actually at a 0.5 degree tilt or even more, and I'll show those different tilts in a bit here. But the point, in addition to its vertical point, there's also the curvature of the Earth underneath it, and both of those factors add up to mean that as you're looking farther and farther from the radar beam is higher and higher above the ground level. That is really important for detecting things like tornadoes that occur. So that's one of the reasons why it's a lot easier for the radar to detect a tornado or a strong surface mesocyclone when the storm is close to the radar, but then as you move here and it doesn't quite see everything that happens down towards the ground. So that's one thing to keep in mind when you look at radar imagery. Notice, I mentioned that there are different tilts that the radar can use, and the lowest one is 0.5 degrees. But each time the radar goes around, it does a higher and higher tilt. It can go all the way up to 19.5 degrees, which is a more aggressive tilt, looking for higher, taller storms closer to the radar. In clear air modes, the radar generally only goes through some of the lower levels. It won't waste time going higher and higher up if it knows that there's no precipitation to look for up there. So in clear air, the radar generally rotates slower. That's easier on the pedestal. It also allows for a higher resolution scan. So it's good to have the slow rotation, especially for like snow or something that's more fine and can benefit from higher resolution. And the scans are generally take longer to produce because of that slower motion. So one full revolution and all the volume scans, all the tilts, will take 5 to 10 minutes. And then in precipitation modes, the radar rotates at a faster revolution rate and scans more levels. Doing it faster, even though it's doing more levels, it only takes 4 to 6 minutes. The scanning pattern is chosen by a forecaster and can be changed at any time. There are automated modes to switch it from clear air to precip mode and then back to clear air after the precip moves away. But we can force it back and forth, and we can choose from different versus general stratiform precipitation. There's something called sales cuts that is especially useful for severe weather, where it will, even of a volume scan, it will come back down to the lowest 0.5 degree tilt and give you that that level at the lowest level, which is very helpful for detecting things like tornadoes or even downbursts forming in severe weather. So sales cuts are helpful and whenever you see maybe during severe weather really rapid scans coming in, that means that we have bells turned on and a forecaster turned that on. Okay, so just to check to make sure you're listening, here's a true-false question. The radar beam stays at the same height no matter how close or far it is from the radar. Is that true or false? I'm going to go ahead and launch that. Go ahead.
Ah, man, I missed the poll. Had to take the trash out. Oh, well. May as well, before they do that.
All right.
May as well click an answer and then I guess try to...
Very good. It looks like 95% of the audience chose false, and that is the correct answer. So thank you.
It is false. I probably
Yep,
should.
as I mentioned, the radar beam gets higher as you move farther from the radar. Another thing that I don't think I mentioned yet about the distance from the radar is not only is that higher, like a pencil, of about almost 1 degree. So here's an example of the same storm on the left and the right, sampled by 2 different radars. In the left example, it's a close radar. You can see, again, this black dot here, that's always where the radar is. So you can see it's very close to the radar. And then this example here, the radar is much farther away up here, well to the north of this storm. And you can see that the
I remember that.
general
I was
structure and the size of the pixels is
spamming
actually
hearts.
bigger, more coarse, and lower resolution. So that is another thing to keep in mind when a storm is farther away from the radar. It might look more blocky, and that's because it is being sampled at lower resolution. You also see that this same supercell
Okay, I'm
on
done.
the lower levels, since you're closer to the radar, you're seeing down towards the surface, you can actually see this more well-defined poke echo in this supercell. Whereas aloft, you can kind of see that there's a mesocyclone there, and there's a little bit of an inflow notch, but you're not really seeing the well-defined hook. Seen close to the ground, and you have to be sufficiently close to the radar to see that. We talked a few times about the little black dot. I'll show it again here. The little black dot here, representing where the radar is, that's actually the cone of silence. So that's yet another thing to keep in mind as far as radar limitations go. If a storm pops up or starts developing right on top of the radar or very close to it, it actually might be in this cone of silence where the radar isn't able to detect it, because I mentioned that the radar tilts go from 0.5 degrees to 19.5 degrees, but they don't go any higher than that. It doesn't point straight up. It doesn't even point 50 degrees or so there's this big white space gap called the cone of silence that will be void of any returns. So this is actually a reason why if a storm is popping up right over the State College radar, we can't use the State College radar to detect it. We'll end up using or the Binghamton radar. We can use the MRMS, which is a composite of multiple radars stitched together, and we can use satellite imagery too to keep an eye on rapidly growing cumulus and cumulonimbus clouds. But the radar itself won't be able to detect it until it moves a little bit downrange or away. And then the last 2 slides I'll show here before I turn it over to Steve. One is a map of radars. So this is Pennsylvania here in the black outline. And you can see that depending on what part of Pennsylvania you're in, there's going to be a different radar that's nearest to you. We cover this central portion of Pennsylvania, so a lot of our area is covered best by the State College. The nearest radar is actually not like. If you look at northeastern Pennsylvania, the York radar is actually closest to that area. If you look at the northwest portions of Pennsylvania, the Buffalo radar is closest. Pittsburgh, that radar samples a large portion of western Pennsylvania best. There's even a little section where the Cleveland radar is closest, and a little sliver down here where the Dover, Delaware radar sees best in southern Lancaster County. So depending on what part of Lancaster County you're in, your nearest radar might be either State College, Philly, Dover, or Sterling. All kind of cover Lancaster County. So that's something to keep in mind. If you're located, you probably want to be checking multiple radars to get the best look at storms approaching you. And this map is a little bit different. The first one showed which radar is nearest to every location in PA. This one shows which one samples closest to the ground. So there's subtle differences here. Typically, the nearest one samples closest to the ground, but there are some nuances where, let's say, for example, the Dulles radar, the Sterling radar, that's located at a lower elevation. They don't have the terrain of central PA down there. It's more flat and low level, closer to sea level. So they're starting their radar beam at a lower level, so they can actually gain ground. You can see compared to the nearest radar map, the lowest radar map is actually gaining ground on that. Encroaching line is, if you want to see lowest to the ground, you might want to look at, again, Sterling for southern PA, Buffalo for northern PA, and so on and so forth. So just wanted to present these maps to you, and you'll have them in your slides as a reference. And when you keep an eye on weather yourselves, you'll know which radar is best to look at. All right, I will turn it over to Steve for this section. Thank you.
Thanks, Mike. Good job presenting. And Mike made those 2 maps that you just saw.
Good
He put a lot
job,
of work
Mike.
into that. So big thanks to him for doing that. So I'm going to go through the different products that the radar
Let's
generates
go,
from the
Steve.
data that it collects. And we'll start out with single pole radar. So this means the radar beam is going out just in one direction. And this is, let's see, Mike, looks like I can't advance the slides. So the legacy radar products, this was single pole. And back when the WSR 88D, hold on. We may have lost the presentation.
Uh
Sorry about that. I
oh.
will try to get that back up.
Okay, that's just YouTube. Ooh, State College. What did you do? Ah, there you go.
Looks like we're back. Let me see if I can advance these. Maybe not.
I hear barking. Does that mean it's dinner time for me?
Okay, now we're good to go. All right, so single pole radar, this is your reflectivity, which shows how much the radar is seeing. This is that the radar is sampling. And then you'll see spectrum width, which is how chaotic is the environment that it's sampling. And these are all the single pole radar things that we have. So this is back when the WSR 88D first came out, this is what we had to deal with. And then modern advancement, which lets us see more, which we'll talk about a little bit later. So reflectivity is basically where is the precipitation occurring and how much are we seeing. It measures the return power back to the radar from the target. So the beam is going out and then coming back to the radar because it's listening for turns. And it's telling us how heavy it is. And it ranges on a scale from -35 to 85. And it's measured in dBz. So the scale there is on the right. And if it's near 0, that's extremely light precipitation. Let's see. Sorry, I'm still losing control here, Mike. All right, so light is greens. Moderates are going to be more of the yellows that you see on there. Precip is when you start to get into the reds. That's around 50 dBz. And then if you get up into the more purpley colors or pink, usually that's really heavy rain. Or now velocity, this is a super useful thing that radar can see. This is the Doppler part of the Doppler radar. The Doppler effect is being able to measure the movement of. So velocity means we can see what direction and what speed these particles are moving that the radar is bouncing off of. So the scale that we use is a green. Red means it's moving away from the radar. So in this example here, central Pennsylvania, here right in the middle, everything to the west of the radar is green, moving towards the radar, and everything in red is moving away. So we can see the speed and the direction from this. And in this case, the wind direction was coming generally out of the northwest. Now the radial velocity, it's the component of the true velocity that's moving directly toward or away from it. So we're not seeing the true speed of these particles in every location, which does make things a little bit tricky. When the radar scans perpendicular motion, the radial velocity will be 0. So if you note in the middle here, you see that gray area. It's not that the particles aren't moving there. It's just that the radar can't sense what speed and direction. Then you're getting the true velocity of that movement. So the best, estimate that we are away from the radar itself. On a perpendicular, that's going to show up as 0. And in that case, we would then look at a different radar to try and get a better
Well, my
idea
sub's here.
of that velocity. So in this example here,
My
on the
sub
left,
is here.
as Mike mentioned earlier,
So I'm gonna go head
the
off to
farther away
dinner. I
from the
hope
radar
nothing
you get,
happens to this
the
stream.
higher up you're actually
I will be
seeing
back.
in the atmosphere. So closer to the radar here, winds are actually coming out of the south. So you see, in this case, it's blue and red. We would normally see green and red, but the blue close to the radar is coming out of the south. So down at the lower levels, that's a southerly wind. And then as you get higher up,
I don't really
farther
want
away
to bother
from the
my
radar,
family
you can
with
see
this,
it's turning
so
more out of the west. So when you see this
I'm gonna
S
turn that
shape
down a
on
bit.
the velocity returns, that's showing the turning of the winds with height. Now, in addition to a case like this, we can also see fronts moving on radar, especially cold fronts. So this is what it looks like when a cold front moves across the radar area. You see this, quick shift in the wind here across the entire area, and out of the southwest. So you see, this kind of straight flow here, and then the winds behind the front are coming out of the northwest. You see that quick turn in the wind. You can see not only cold fronts, but also outflow boundaries from thunderstorms and things like that. You can really tell a lot from velocity. And also, we will look for certain signatures from storms. This is a downburst signature here, and kind of subtle, but if you see the red next to the green, it implies a wind shift. And then we'll look at the direction that these particles are trying to tell what we're seeing. So you can either see convergence or divergence with this. In this case, notice that we have this little area of red, which means it's moving away from the radar. And then we have green, which is moving towards, and then so you kind of get this idea that it's spreading out, and that's a downburst signature there. So the wind is spreading out as it hits the ground. Now, in this case, we're looking at so look on the right here. You see the pretty bright reds here, and then the greens. So you can get a sense; those are right next to each other, and the radar's down here as well. So you can kind of get an idea that this is this is spinning, this is rotating here. So we'll look for those signatures for sure. If we're looking for mesocyclones and tornadoes as well. We typically wouldn't actually see the tornado itself from the radar unless it was really close to the radar.
I gotta turn
But we
that
can get
down.
a sense for how strong the mesocyclone is and
Okay.
the velocity.
I am actually going to go eat my sub now.
And then a little bit more looking at the velocity signatures. So again, this is looking at a rotating thunderstorm. So you see reflectivity. First, you want to look for that to know that what you're sampling is actually real and actually there. And then you look at the velocities, and you see, very strong winds right next to each other, going away from the radar and going toward the radar. So this is what we're looking at is very strong rotation. This is 100 knots of gate-to-gate shear. So, this is very likely a very strong tornado. And this would require a warning for sure. So this is what we're looking at when you hear either the term radar signature. This is what we're looking at. It's called a couplet. And the stronger that is, the better idea you have that there's a tornado going on or that a tornado will happen soon. Now, the third component of single radar is spectrum width. And this is looking at variability of motion. So how much does the Doppler velocity vary within one of those little radars? And a higher spectrum width means there's a lot more variation in that velocity. And it can indicate either really turbulent motion, a lot going on in that bin, but also can show places where maybe we have data quality issues. So this can be kind of useful to diagnose if what you're looking at is actually happening or if it's, more just in a circle. There's really not much reflectivity. Velocity looks wrong, and this would look like a rotation couplet, maybe something that would need a tornado warning on. But if you look at the spectrum width and that kind of lighting up, that gives you an idea that something's going on here that isn't, it's not quite right. And what we're actually seeing is called side lobe contamination. So like Mike mentioned earlier, the radar can look up different levels. Sometimes it can think even it's seeing something higher up in the storm, the rotation, but it can plot it in velocity on the lower scans. So it can kind of trick some people into thinking that there's rotation that really isn't there at the surface. So you want to make you have reflectivity if you have velocity. Otherwise, you might be looking at side lobe contamination, which we actually see a lot on the radar in this area. So it's something that we look for. But spectrum width kind of gives you an idea that maybe what you're looking at isn't good data. So another poll question here. True or false, single pole radar products, aka the legacy products, can reveal information about particle shapes? So we'll let that go for a minute. And Mike, I can't see the results, so if you want to jump in when you have them, or I guess they might pop up on the screen.
Sure, I can read them out when they come in. Looks like we have about 68% voted so far. Any last votes? A couple trickling in. All right, I'll go ahead and share them. We had, let's see, 74% said false, 26% said true.
So single pole cannot see the exact shape of what we're looking at. So that is false. But luckily, we now have dual pole radar, which came about in the 2000s direction. Now dual pole, it goes out that we're looking at a horizontal scan of the particles and a vertical scan as well. And you can tell a lot of information from having a lot of new techniques and tools that we can use now to diagnose, what we're looking at with the radar. Let me just, pole was just going out in one direction. We were just looking at the horizontal scan of particles, and now with dual pole, you get the horizontal and the vertical. So now we can tell a lot about the shapes of what we're looking at in the atmosphere. Okay, so whereas before we had reflectivity, velocity, and spectrum width, differential reflectivity, the correlation coefficient, and the specific differential phase. And I'll go through each of those and what they mean here. So differential reflectivity, also called ZDR, it's the difference between the return power from the horizontal and the vertical planes. So we're looking at the horizontal orientation and looking at the vertical, taking the difference of those, and that will, if we're looking, if it's something about what we're looking at just from those measurements. Correlation coefficient, looking at how similar things are in the radar echoes. And Phil just gave me a note. Dual pole, 2017 was that when ours upgraded. So our radar was upgraded in 2017 to dual pole. So this hasn't been around, for that long, which is exciting because now we can learn a lot from this. And then we have specific differential phase, or KDP, and this looks at the amount of liquid water in, and we can tell a lot from that is, are we looking at rain, or are we looking at hail, things like that. So we'll kind of go into each of these here in more depth. So ZDR is looking at what shape are the particles that we're hitting with the radar. So if it's a sphere, then ZDR will be it's wider in the horizontal plane, then you'll look at values. Things that are more spherical, let's see here. Oh yeah, and this is on the right. All right, so spherical, these could be particles of any size. They'll show the same, but if it's a sphere, this is what it will return. So drizzle is really, really small particles, but they are generally spherical. And hail can be extremely large, and it also looks spherical. So those will both show 0 in the ZDR fields. Now, if we look at non-spherical particles, that we're talking about If it's in the horizontal, we're looking at more of raindrops, because although, raindrops always get depicted kind of as like coming up to a top, and then, they're wider than they are tall. So this will show up more on the horizontal axis than the vertical. And then snowflakes as well, as they fall, especially if they'll kind of drift down, and you'll see them more in the horizontal versus the vertical. So those will be positive ZDR values. And then things that are more vertical, grapple is one. It's more of a cone shape, so it's taller generally than it is wide. So you'll see that show up as a negative. One application of using this is what's called a ZDR column. So the updraft of a thunderstorm, a strong thunderstorm, will contain large liquid drops. So we'll get a higher ZDR value because there's more horizontally oriented things that we're bouncing off of. And then the surrounding will be comprised more of ice particles, small hail, grapple, things like that. You'll get a lower ZDR value. So what you'll end up seeing is this area on the radar that really stands out of the ZDR. Oh, hold on there. So the radar scans up in the storm, sees that area of what's more raindrops, kind of surrounded by, by more ice crystals, snow, things like that. Ice crystals, grapple, and you'll actually end up seeing this this little area here. You can see my pointer. This type particles. So this will really stand out drawing updraft of a thunderstorm. That's one thing we can. Also, this is useful to detect hail. So on the left is reflector, just bouncing off of things and seeing how much the radar is seeing. But on the right, this is ZDR, and all these, red values that you see here that are very positive, this is all raindrops or large raindrops. But then all of a sudden you see this drop around zero, and that looks really weird. And what's actually seeing the round hail in this area comes out, around zero for ZDR. So although from reflectivity we could see, all right, that's really high, maybe that's not a rain. It's possible it could have been just heavy rain. But in the ZDR, you can tell that what you're looking at is hail. So that gives higher confidence when you're issuing warnings for hail that you do have, the hail. Poll question here, just for fun. What is the ZD of this cow? So remember, it is wider than it is tall. So what do you think the ZDR would be?
And assume that the cow is not flipping through the air. It's just staying just like that, horizontal.
Stationary cow.
Looks like we have half the audience voted so far. Give another couple of seconds. All right. So we got 62% say greater than 0, 12% say 0, and 26% than 0.
All right, so most of you got that right with the positive ZDR. If the cow was flipping through the air and tumbling really fast, then it might have a ZDR to 0, which can happen with hail sometimes, it'll tumble. But in this case, or I guess if the cow is tipped up vertically, then it would have, in this case, stationary cow, it's a positive value. Now we'll try another one here. What's the ZDR of this corn cob? And assume that this is stationary and just standing upright.
All right, looks like, and we've got 90% say less than 0.
All right, good job. That is correct. I can click, yep, here we go. So what is the ZDR of this basketball?
Even better this time, 95%. Say 0.
All right, good job. You guys are all ZDR pros now. Okay, so specific differential phase. This is called, for short, we call it KDP. And we're looking at how much liquid is there. So this is the amount of non-spherical stuff in the sampling volume. So positive KDP indicates there's a greater the horizontal than the vertical, meaning larger volumes of large raindrops or water-coated hail. So it's kind of like reflectivity, but only for things that aren't shaped like a sphere. So this one's a little bit more complicated of how it gets measured. Let me see. There we go. So as the beam moves out, the horizontal will slow down a little bit more than the vertical will, and you can measure that difference and get the KDP. So it lets you know how much liquid is the beam moving through of that energy that gets returned. So that horizontal and that vertical, looking at the difference in the energy return of those two components, and that lets us know how much liquid is it moving through. So what it ends up looking like on radar is you'll get these, so reflectivity is on the left and the KDP is on the right, and you see it really stands out when this lights up. What you're looking at is really heavy rain, or there we go, large amounts of small melting hail will also show up like this. So you kind of get an idea of what you're looking at out of this. Stand out pretty clearly here in this example, and this was here state was example really close to us here. I'm at the office, so you're looking at really heavy rain, or maybe accumulate, and sometimes in the plains you'll see this. Like I've seen pictures in Texas of the feet and feet of accumulating small hail, and they need to get plow trucks to clear it out. This would show up really clear in there. And then one more here, which if any of you are a little more radar savvy, especially of what to look for maybe with tornadoes, you might have heard of the correlation coefficient. It's one way that we can detect debris balls. So, and Mike will go into that later. But the correlation coefficient is looking at how different is the stuff that the radar is looking at. So it's uniform, rain, all snow, then you'll see a high correlation coefficient. Everything will kind of look the same. Melting snow, things that are a little bit more chaotic, correlation coefficients. And then if you see something that's non-meteorological, which we do see a lot, birds, insects, or debris, that'll be a very low correlation coefficient. So this is another way that we can kind of tell if, one, what we're looking at is real, or is meteorological, and then two, we can kind of get an idea of what we're looking at with the radar as well. Here is an example of sampling the melting layer with the radar, or a bright band, and you have strong differences between ice and liquid water, and that means you can see the phase transition really clearly on the correlation coefficient data. So remember, like Mike said earlier, the radar beam goes up higher as it travels farther away from the radar. So down here, we're seeing all liquid. Up here, this is the freezing layer or the melting layer. And then out here, we're seeing all snow or ice particles. So you can tell, that this band is where we're seeing the melting or the freezing occurring. And if you know how far away you are, and you know the estimate of where the beam height is at that level, then you can figure out the level or the elevation at which the melting layer is at, altitude that's at. So this could be really, really useful. So why a ring? So imagine that you have a uniform 0 degrees Celsius layer. So that's, the melting layer in the atmosphere. Below it, you have all rain. Above it, you have all ice particles or snow particles. And the radar beam, as it goes out, tilted up, and then it goes around, it's going to scan, in a ring through that layer. So it will show up as a ring. Closer to the radar, you're going to be seeing the rain. And then farther away from the radar, you're going to see the snow. And that's why it will show up as that mixed ring. So this is kind of a side view of it. The beam, going up, looking down below, seeing all rain, those hamburger-shaped particles. And then it gets more chaotic at the freezing level here. So you're seeing a mix of rain and snow. Maybe it's water-coated snow, things like that. And then once you get above snow, are all ice particles. So you can tell the melting layer from that. And it's not always a clear-cut ring. A lot of the times it is, but sometimes it'll be a little bit weirder than that. And you can kind of get an idea that maybe the melting layer isn't just a perfect, flat level, which it almost never is. But maybe you have something else going on, like in this case, a cold front moving through. So right along and behind, it's already below freezing all the way down to the surface. Whereas out ahead of the front, it's above freezing. So you almost get like half of a ring here, and then right down to the surface here, closer to the surface, and then behind it, you're looking at all uniform, in this case, probably no particles. And then it's also very useful, not only to, just see where the rain snow line or things like that is, but also in the warm season, you can see differences as well. So you can see the low correlation coefficient. This little bit of the half ring here is the melting layer, but you can also see hail. So this severe warm storm here, look how most of the storm is uniform. Right here where the hail is falling, you kind of see the values drop out. So that gives you an idea that there's, something else going on. And if you were already looking at the storm and looking at the reflectivity and, all that and thinking, oh, this could be severe, and then you see a hail signature like that, then you know that there's hail in that storm. So correlation coefficient is really useful. And then this is a really cool case from back in 2020 in Philly and Trent, so Southeast PA, New Jersey. And look at this ring going out away from this cluster of storms. And notice how it's, it's not red or it's not orange, but it's blue. That be. So we have thunderstorm outflow. So the cold, dense air is hitting the ground and it's spreading out. And the outflow, it's windy, it's chaotic, it picks things up, and it's actually moving a lot of, in this case, probably bugs. So we're seeing bugs on the radar here. One, you can see them in the reflectivity. It shows up as that ring. That's, not rain in that ring. That's probably little bugs and things like that. But then in the correlation coefficient, you see that blue, so that means it's a really low value. So that then we know that what we're looking at is biological. So it's most likely bugs. And you can also see this other times, bird rings, or sometimes bat rings. I think but you can see bird in the evening. It's kind of cool. Sometimes that'll like make it on the news. People get really interested in that. So another poll question here. What causes the melting ring that we see on the radar?
All right, I'll close the poll. It looks like we have 92% for a combination of snow and rain.
All right, nice job, everybody. That is correct. And then one other thing we'll go through here is hydrometeor classification. So we can get an idea, from the radar of what it's, and then it'll put it into these categories: rain, biological, ground clutter. Those are on the left. They'll be gray. And then we get from ice crystals and snow, all the way to
Alright, I am
rain,
back.
heavy rain, and then big drops, graupel, and hail. So it'll put it into these bins and then kind of show you, on one display of what the radar
Alexa,
this is a
ASH.
case study from Binghamton's area. So you see a lot of light green, so that's just general rain. Some pockets of dark green, which is heavy rain. Red, which is hail/rain. And then as you get farther away from the radar and it's seeing higher up in the storm, look over here on the edge. It's light blue and pink. It's picking up the snow and ice crystals farther away from the radar. So going through, each of our radar products that we have here. So on the right, we can look at the reflectivity here. Notice the greens and yellows, light rain. And as you get farther away from the radar, in this one here, it's picking up some snow or ice crystals. As you get more into the reds, maybe even some pink or purple in there, that's more of your heavy rain and your hail. Correlation coefficient. So a lot of this looks pretty uniform. So it's sampling mostly rain. But maybe in a few of these heavier ones, could be a little bit of showing up. And then farther away from the radar, a little bit of the edges. Differential reflectivity. So, looking at the shape of the particles, looks like mostly positive values. So we're looking at those hamburger-shaped raindrops. Right in the middle of this bigger guy, maybe there's a little bit of hail there where it's dropping out some. And then the specific differential phase, we're looking at the pockets of the heavier rain, which really stands out, pretty quick. And, maybe some hail in here as well. And that is it for my part. So I will pass it over to Mike.
Mike is back.
All right, very good. Thank you, Steve. And looks like we're doing good on time. This is a little bit past the halfway point for this presentation. So a little bit more than 5 minutes. How about we resume at 7:15 p.m. I'll give you guys about 7-8 minutes to take a break. And then I will also answer any questions that come through the chat during that time, and we will resume at 7:15. Thank you.
Okay, guys. We are in our break now. So that means I can grab the stream for a bit. I can grab all of y'all for a bit. Oh, holy cow, this is hot. This is actually doing pretty good on battery, so anyway. But anyway, obviously, guys, there's our break. We will resume at 7:15. It's currently 7:08, which apparently I need. It's hot in here. So hot in here that I have to clean the camera. Now, I know y'all can't see it, but I'm gonna have to keep the room like this because it'll probably doesn't seem to get very hot when it's like this, which is, well, good, but stuff like that. So we are on our break right now until 7:15. Then I will resume the normal stuff that State College is teaching you. So if you guys have gotten anything out from it, be sure to let me know. If you guys got anything out of what they were pretty much talking about there. Anyway, you found out Palm Beach County was under a tornado warning and a truck got flipped. Dang, Southwest 147th Avenue. Dang, that's crazy. That's crazy. So now pretty much I'll be able to answer your chats for a bit until 7:15 when we get right back. So yep. So we can put more of the light. We can put the light on for a bit so there's a teeny bit more light here. But yeah, that's kind of better. We don't have to be in this dark room anymore. But this light's working in again because I don't have my school iPad anymore. So we can put the lights on. But nah. We're going to be turning a light off again soon because, well, we're doing this webinar thing. That's what State College pretty much has been talking about this entire time so far. I don't know if they ever covered this, but we're looking at severe weather radar applications. I guess that's what we are looking at. So yep, been on for a little bit over an hour and 10 minutes here. So yeah, that's pretty good. I mean, this stream is gonna pretty much be going on until the end of the presentation of NWS State College and stuff like that. So once they start, I really do hope you enjoy the second half, as again, I will be watching the webinar. I will not really be on the chat looking at y'all. So yeah, during this break, why don't we check in with every radio except the two over there, because I had to stack them on each other.
Lows in the mid-40s. Northeast winds 5 to 10 miles an hour. Saturday, mostly sunny.
Sounds good to me.
In the mid-70s. East winds 10 to 15 miles an hour. Saturday night, partly cloudy, then becoming mostly cloudy between 8 p.m. and 4 a.m.
All right, that's pretty good.
East winds 5 to 10 miles an hour. Here is the latest national.
Yep, later than Saturday.
Lows in the mid-40s. North winds 5 to 10 miles an hour.
So, yep.
Highs in the lower 70s. Northeast winds 5 to 10 miles an hour. Friday night, mostly clear. Lows in the mid-40s. Winds 5 to 10 miles an hour. Saturday, mostly sunny. Highs in the mid-70s. Northeast winds 10 to 15 miles an hour. Night, mostly cloudy. Lows in the upper 40s. East winds 5 to 10 miles. Here is the latest National Weather Service forecast for Schuylkill County, including the city of Pottsville. Tonight, mostly clear. Lows in the lower 40s.
All right, and then the HH54 over here.
Highs around 70.
Yep, that sounds good to
North
me.
winds 5 to 10 miles an hour. Friday night, mostly clear.
Alrighty. Did any of you enjoy the video I posted last night?
Saturday, mostly sunny. Highs in the mid-70s. East winds 5 to 10 miles an hour.
Alright, that sounds pretty good. So yeah, did anybody enjoy the video that I uploaded yesterday of the Skywarn stuff? So anyway, yeah, let me know if you like the Skywarn stuff that I uploaded yesterday. I mean, I just decided to do that anyway, just to show off the Skywarn stuff. So, yeah. So, we're about to get started. Minutes we get started, so, again, with the second half of this webinar. So, yep, that is right. We'll resume at 7:15. It's currently 7:13. So yeah, like a minute and a half, almost about a minute and a half. Yeah, and then pretty much that'll, after the webinar ends, obviously is when the stream will end. So, hope you guys are enjoying this stream here. And, yeah, I mean, that was a good little walk around, I guess, and check up on the radios and stuff like that. So we'll continue with this, with the severe weather. I really hope that, I'm going to put Do Not Disturb on. I really do hope that that can maybe, I even have Do Not Disturb on here, which I think I do. Yep, I do. Okay, great. Now Do Not Disturb is on. Hopefully no notifications pop up there. I meant to do that earlier. 7:14, so we're going to get started here again with State College's webinar, because they're going to get started here shortly. So I do hope you guys enjoy the rest of this. And yay, now I get to flip and play with this again. Alright, that's just going to have to be work. Well, that's just pretty much going to have to be what it looks like, so.
Okay, I have 7:15 on my watch now, so we will go ahead and resume the presentation. This last section here, this is going to be severe weather radar applications. I think the idea here is mainly to get you all familiar with the thought processes that the forecasters have when we make warning decisions in severe weather. So we'll show a bunch of screenshots and talk about the thought process. Different ways that we can get severe weather, and one of them is discrete individual cells. These are often seen in the summertime, maybe a lower wind shear environment where stuff grows vertically, and you'll get a thunderstorm that develops and maybe lasts about half an hour to 45 minutes before it eventually collapses on itself and dissipates. A lot of those storms are not severe because they don't have that wind shear to separate the downdraft and the updraft and allow that storm to become mature. But they can be briefly severe. We call these pulse severe storms. They can be a little bit difficult to forecast, and when we are watching them on radar, we really have to take your eyes off it all. We almost call it whack-a-mole kind of radar look to it sometimes, where stuff just goes up and down really fast. You get the growth and then the decay, and briefly in there, it might be severe. So a couple of the things that we look for, one is this essentially like an inverted triangle, inverted pyramid signature that we might see in a vertical cross section. So what this is here, this radar image is actually not like we showed in some of the earlier images. This is a cross section. So you actually draw a line through the thunderstorm and then look at the vertical. So the surface is at the bottom, and then let's say, for example, maybe this is every 10,000 feet there's a line, or every 20,000 feet, so on and so forth. And what we notice in this picture is the reflectivity values getting greater as you move up, and they're highest in the middle and upper portion of this storm, and the storm gets wider as you go to the middle and upper levels of the storm. So what does that mean? That means that there's probably a hail core, or at least large raindrops built up in that storm and the big is, and the heavier it is, the more likely we are to eventually see a downburst fall out of the storm and see severe winds, only briefly, as the storm, again, it's pulse. It won't last very long. So that's one of the signatures that we look for. We do like to draw cross sections using and it's another way to look at radar imagery. So that's something we can do. We can also look at isothermal reflectivity. So what that is doing is the MRMS that I mentioned earlier, multi-radar, multi-sensor is what that stands for. And that uses multiple radars and stitches them together, and also takes in other meteorological fields for the development of hail. And we can look at what the radar reflectivity is at that level. And when you start to see numbers like 35, 40 dBz, and especially 50 dBz plus, that means that there's probably hail up at that level, and it's a strong updraft enough to support the hail, and probably this is going to be a severe storm. So yet another way that we can take radar imagery and combine it with some other meteorological data, like the temperature aloft, and get something even more useful. Another thing that we often see in especially summertime convection is something called a hail spike. And this is what they look like. You can see this one forming on the south side of this supercell thunderstorm moving through McConnellsburg here. I'll play this through again. The radar in this case is the State College radar, located to the north, well to the north of this frame. And you can see that I'll pause it here. There's the higher reflectivity values, which is the storm itself. And then there's kind of this tail, looks like the tail on a comet or something like that, where there's like lower reflectivity values that kind of taper and getting deflected down towards the ground, and then going back up to hit the hail core and then come back to the radar. I'll explain it more in this next slide here, because it is pretty interesting. So what's happening in a three-body scatter spike? It's called three-body because there's three bodies in this problem. There's the radar itself,
The iPad hot.
there's the hail up in the thunderstorm, and then there's the ground. What happens is, like any other pulse, it goes out
was hot.
from the radar, it hits the hydrometeor, in this case a big hailstone, And then that hydrometeor, because hailstones reflect energy really, really brightly because they're big, they're solid, they can really absorb that radar energy and then reflect it back. It doesn't just reflect straight back to the radar, it goes out in all directions. And a component of that actually goes straight down and hits off the hailstone, hits the ground, and then it's still so strong that it can bounce back up to the hail and then come back to the radar from there. So because that path length is longer, because it's going not just from the radar to the hailstone and back, path length is longer, it's going from the radar to the hailstone, to the ground, to the hailstone, to the radar. That takes more time, and the radar, when it does its ranging process, it thinks that that return is farther away. So that's why it places it, if you look back at this image, radial of the thunderstorm itself. Because, again, the path length is longer, it took longer for the return to come back to the radar, so the radar thinks it's actually farther away. Bottom line is we can use this, what is actually a radar artifact, as a tool for detection. So it's almost ironic that it's something that the radar wasn't designed to do, but it's cool. So perhaps you've seen that in the past and didn't know why it occurs, and hopefully that explains why we get those hail spikes. So we talked a little bit about individual cells and hail spikes. We'll talk more about supercells next. Supercells, they tend to be longer lived. They occur in an environment with shear, and that shear separates out the updraft and the downdraft. So the updraft stays upstream down near this hook echo, and the downdraft ends up being towards the front, forward flanking downdraft. And these supercells, they also updraft, and that lowers the pressure within the updraft itself, because anytime you have rotation, you have low pressure, in the mesoscale at least. So you end up with a long-lived supercell, and a lot of these end up producing severe weather. About 80% do produce severe weather. Only 10 to 20% produce a tornado. That's actually probably closer to 10%. Supercells often have a hook echo that we can see on radar. But what exactly is that hook? We're going to talk a little bit in whether some of these classic hook echoes appear on supercells.
Heck yeah.
What it is actually this intersection of the rain-free inflow area, which is shown here in the yellow, that's the warm and humid air that's being sucked into the updraft. And where that meets up with the rear flank downdraft, which is shown here, there's actually two downdrafts in a supercell. There's a forward flanking downdraft and a rear flanking downdraft. And where that RFD, or rear flank downdraft, meets up with the inflow node, the hook echo. And there's not always a tornado there. The hook echo is indicative of a strong rotating mesocyclone, as well as a strong updraft, but not necessarily indicative of a tornado. It can mean that a tornado is favorable, especially if the environment is one that's good for producing tornadoes, where it has a low LCL, which means the clouds are lower down. That will happen when there's higher relative humidity. So if you have high relative humidity, low LCLs, and you have the right amount of streamwise vorticity, which I won't get into in this presentation, but it was talked about a little bit in the previous advanced Skywarn talk about severe storms. If those ingredients are there, then yes, you might see a tornado be produced in the hook echo. One more point that I'll make, I think Steve mentioned it earlier, usually when a tornado itself, it usually sees that strong mesocyclone, and then the forecasters have to make inferences about that mesocyclone and the environment it's in to gauge the probability that a tornado is forming with that hook. But occasionally those hooks can be close enough to the radar where the radar gets to see it in higher resolution and closer down to the ground, and can actually measure the tornado, sample the tornado itself. But that's fairly rare. Okay, so we talked about hook echoes. Next thing to talk about is related to that. It's a bounded weak echo region. So now we're going to look at a cross section again here on the left. So this is a vertical cross section. The surface is at the bottom, and we're looking higher into the atmosphere as you go up. These numbers here, I believe, are in, you can add 3 zeros and they're in feet. So up to 43,000 feet up here at the top region. We call this a BWER, BWER, BWER. That's also indicative of a strong updraft. You can see where this cross section was drawn through, and there's the hook echo there. So the point of this is to show that the hook echo is not just a two-dimensional entity at the surface. There's actually kind of an indication aloft too for the lowest, about 15,000 feet, and it depends on the strength of the updraft. The stronger the the taller that B word can be. But yeah, it's essentially the reflection or the vertical extent of that hook echo, the bounded weak echo region. And again, this is, when we see this, we will lean more in favor of either a severe thunderstorm warning or a tornado warning, again, depending on that environment. And if we got a spotter report of a funnel cloud, that might nudge us towards a tornado warning. But this is an indication of a strong rotating supercell. And these are just here of cross sections and supercells. Most of a supercell's large hail falls on the forward flank downdraft, so just to the north of that bounded weak echo region and the inflow notch, the hook echo. And that's because it's just down shear of the updraft. The updraft forms in this weak echo region, and then the wind shear carries those hydrometeors, the rain and the hail that's forming, carries that downwind or down shear. And the radar cross section, again, is a very useful way of looking. We're going to look a little bit more into the supercell and look at the different the radar parameters that Steve introduced and spoke about earlier. So the top left, we're looking at the reflectivity. In this case, in this white circled area, we're seeing reflectivity of 55 to 73 dBz, which is quite high. The ZDR, your ZDR values here are between -2 and 2. And remember, that shows whether or not the features, the hydrometeors, are more oriented in the horizontal, the vertical, or spherical. In this case, between 2 and 2 is centered on 0. So roughly, these are probably going to be in the atmosphere. The KDP, that measures the amount of horizontally oriented, essentially wet stuff in the atmosphere, and those values are pretty high especially to the south and to the north. That probably means that there's some small melting hail or maybe even some heavy rain on either side of that really heavy reflectivity. And then the last thing here, bottom right, is and this is a reduced, it's not quite as low as you would see for something like bats or birds or bugs, not that low, but as far as meteorological hydrometeors go, 0.7 to 0.9 is low. It means that there's going to be a mixture of different things in that sample. In this case, probably some hail, some wet aggregates, some wet ice crystals, and some melting. So a lot going on in here, but my question for you is, what is radar detecting in this white circle? Is it just heavy rain? Is there a tornado? Is it hail, or is it heavy snow? And I will launch the poll.
Uh-oh. Oh boy, let's see. I'm still not good at radars, but let me take a wild guess. I would say, so
I just noticed that the poll responses, somehow we got a different option in there that's not in the slides.
let's just give it a whirl.
But it looks like the majority of you are choosing hail for this one, which is the right answer. It's mostly hail.
Is it? Okay.
But there also is heavy rain, and you can. It's a mixture of hail, definitely hail, and some heavy rain around it as well. So good job with that. Okay, we'll talk a little bit more about supercells. Now we'll talk more about the how we actually detect rotation. So back to that velocity parameter. In this case, the white dot represents where the radar is, and rotation, like Steve said, is going to be measured by when you see this juxtaposed greens and reds next to each other. So green is motion towards the radar, and red is motion away from the radar. And you can see that there's kind of a broad sense of rotation, as well as because this tornado happens to be close to the radar, you're seeing the tornado couplet as well. So in this case, you get to see both. And this is what the reflectivity looked like here in the yellows and reds. So you can really see that hook echo. You can get a sense of the size of the mesocyclone. And the tornado itself, the whole hook is more representative of the mesocyclone, but it's tucked within there. So that would be a tornado vortex signature, that tight couplet there. So next question here is a true or false. We didn't talk about it yet, but we will. The question is, there we go. Question is, every tornado produces a tornado debris signature. True or false? Yep. Answers are coming in pretty quick.
I don't know. It's
And for
probably
this
false.
one, we got 86% saying false and 14% true. And those who selected false, that is the correct answer. Not every tornado produces a tornado debris signature. It can happen occasionally, and we'll talk next about how to identify them.
By the
So
way,
it's a
I purposely
multi-step
clicked the wrong
process.
answer
First,
to
you
see
want
if
to
you guys were
identify a
watching.
valid velocity circulation. So that's using that radial velocity, those greens and reds that I showed in the prior image. The next thing you want to look for is correlation coefficients that are less than 0.85, and they have to be co-located with that circulation. They can't be in a different part of the supercell. They have to be right on top of that couplet. Third thing you want to look for is sufficient reflectivity, greater than 35 dBz. That has to be co-located as well with the rotation and that differential reflectivity, the ZDR near zero. So go through each one of these images. So this top right one, that's looking for that couplet in the velocity. So that's a velocity circulation right there where the green meets the red. So we've identified that. Step 2, the lower CC values, they are co-located with the circulation. So that's a check mark there. Number 3, that reflectivity has to be above 35 dBz. In this case, it definitely is. It's much higher. It's probably 55 to 60 dBz, potentially indicative of a debris ball or at least some rain being wrapped around and probably some debris as well into that circulation. And then number 4, a lowering of the differential reflectivity ZDR to near zero. And that you can see in that black circle there in the bottom left, the values are lower there. And the reason for that is when there is debris lost actually tumbling through the air, because if it was, you take something that has ZDR normally greater than zero, and then you start tumbling it, and to the radar, it looks like a sphere at that point. So ZDR ends up being zero. For tumbling, turbulent things, the ZDR tends to be near zero, and that's what we're looking for the tornado debris signature, because that debris is chaotic. And that chaotic nature, that's also why the correlation coefficient is how you find a TDS or tornado debris signature. Sometimes on social media, we'll see in real time people point out little areas of low correlation coefficient that they think they're worried that it's a TDS, warning their friends, hey, this might be a tornado. But in some cases, it doesn't match up with where the rotation is, or it could be in a spot where there's no reflectivity, and those are not TDSs. So just be careful how you identify them and make sure you follow the steps. And here's a real world example, another one here. This was actually from our CWA. We don't see TDSs very often, but occasionally we do. And this is an example of one from October 2nd, 2018.
I remember that day.
From the radar, so it wasn't the best example ever, but you can see that there's an area of rotation here, and you can see the couplet and the velocity signature. The CCs they're definitely messy. You can probably argue that this is indeed a TDS and a lowering in the CC associated with the tornado, but you can also argue that maybe this is just noise. Again, this is not a great example, but we don't get many examples to begin with in our CWA, so I just wanted to maybe you can all find some better examples as well. And yeah, so the next thing we'll talk about is, again, not all correlation coefficient reductions are associated with tornadic debris. Those first three criteria must be careful with that. This is another example of some other things that might lead to reductions in correlation coefficient. One is hail. You can see that here. Another is actually the hail spike itself can lead to lower CCs. And again, that's because since the radar is hearing the ground, well, that's going to look pretty different from a reflection that's coming from ice crystals or hail. It's going to look pretty different to the radar, so that leads to that reduction in CC as well. Okay, so next we will go over some things about QLCS storms. So QLCS stands for quasi-linear convective system. It's essentially a line or something that looks, the word quasi means essentially similar to or looking alike. So it doesn't have to be a straight line. It can be a complex of thunderstorms. And this is an example of one here on radar that came through central Pennsylvania in early June of 2020. This was on June 3rd in the morning to early afternoon. This was actually classified as a derecho, meaning that it had very strong winds over a large swath through Pennsylvania and New Jersey as well. It actually came through State College, but it wasn't very severe at the time. It was kind of marginally severe. Where it got really intense was far southeastern PA, just around the Philly area, and then especially into New Jersey, where there were a few hurricane-force wind gusts that were measured. This picture here, I believe, is from a different storm, not the same storm, but essentially what you would probably see on a QLCS similar to this. You would see a shelf cloud, which delineates the leading edge of the outflow from the thunderstorm complex. So to the right is ahead of the storm, and to the left there behind the shelf cloud, that's where you're getting precipitation coming down, a lot of rain-cooled air, and right underneath that shelf cloud is often where the strongest winds are. So for a system, what kind of things can we look for on radar? Well, one of my favorite things to look for is a mid-altitude radial convergence signature. This is an example of one here. So in this case, the off the screen up and left of the squall line, or QLCS. So the red's, that's air moving away, green is air moving towards. So this is a strong signal of convergence. But this is right at the surface. This is actually a mid-level tilt, about 10,000 feet above the ground. And when you have converging air in the mid-levels, come down and then eventually hits the ground and spreads out. So that convergence in mid-levels is actually a very good indication that there's probably divergence at the surface in the form of, in this case. So we'll use this as an indication to warn for severe winds in an area farther away from the radar where we can't actually sample what's happening at the ground. Maybe the lowest beam height is 6,000 to 7,000 feet above the ground level and we can't see the ground. Well, at least we can see the mid-levels. And if we have a strong mid-altitude radial convergence signature, which we call a MARC for short, that's a good indication that that's probably it. And then hand in hand with that, there's also the rear inflow jet, which was probably spoken about at least a little bit in the advanced Skywarn talk back in March. But the bottom line here is that this is a way that a QLCS or a more linear feature can become bowed. It starts to take on this bow-like structure where one part of it surges out. And that's due to a rear inflow jet developing. And what that is it's an area of very fast winds from behind the QLCS and then surging out to the front. And what actually causes that is the warm updraft induces a low pressure area in the middle. The reason why it's low pressure is because it's thermally it's warmer than the surroundings, and that creates an area of low pressure. And it's a warm updraft because hot and humid air from the surface into the updraft, and so that creates low pressure. And the low pressure essentially sucks in air from behind because air moves from high pressure to low pressure. That's how you get any kind of wind. And in this case, you end up with a mesoscale enhancement, a narrow jet of strong moving, strong winds drawing in air into that low pressure area. And that's how you end up with these rear inflow jets. This is what they look like on radar. So you notice not just the reflectivities bumping out at the front end, but also this kind of lower reflectivities moving in behind the storm. And one of the reasons for that is that these rear inflow jets, they descend. You can see it in this diagram here. So this is another cross section on the bottom left. Actually, they both are. So the greens, yellows, and oranges here, this is all reflectivity. And then I'll switch it to this slide. This is velocities. So you can see this arrow that's labeled A shows that the rear inflow jet doesn't move just horizontally. It actually descends. So it's coming down, and descending motion in the atmosphere is a drying phenomenon. Back end of that hook. Of the bow. So you end up with the descending rear inflow jet causing lower precip rates and lower reflectivities in the apex or the back end of that. Like this, there's probably very strong winds with it, and as long as there's no inversion near the surface, those winds are likely getting in really severe fashion. QLCSs are often wind producers, as we were just talking about, but occasionally they do produce tornadoes as well. About 20% of all tornadoes are associated with QLCS systems. The other 80%, mostly supercells. Compared to supercell tornadoes, the QLCS tornadoes tend to be shorter lived. They don't last as long. They're usually on the ground for anywhere from maybe 30 seconds to a minute to maybe as long as about 10-15 minutes in like an extreme case. But really, especially in Pennsylvania, most of these are on the ground for just a couple of minutes. So they're rapidly developing. They're on the ground for a short peaker side too. A lot of EF0s, EF1s, and occasionally EF2s, but those EF2s tend to be kind of a hybrid between a QLCS with an embedded supercell structure within it, where you can actually see a hook echo and kind of a discrete cell within a line. But yeah, the QLCSs develop at night. They can happen all times of year, even in the wintertime. Pretty much any time you have a high shear environment with just enough cape, you can get a QLCS to form. And if there's enough wind shear along that boundary, there can be a few spin-up tornadoes. So when you see a QLCS or a linear squall line come through, the primary threat to keep is wind and lightning, but also there is a tornado threat at times as well that can't be ruled out for linear systems. To warn for QLCS tornadoes, we look for the portion of the QLCS that's aligned perpendicular to the low-level shear. So this is getting kind of into the weeds. If you're really into weather, maybe you'll care more about this, but I won't spend too much time on it. But essentially, yeah, we're looking for the part of the QLCS aligned perpendicular to low-level wind shear vector, rotation near the apex of the bow, a descending rear inflow jet behind it. So that's, again, this lower reflectivity into the backside of the bow. And then other typical tornado indicators like a couplet, a TDS, any of that, those would nudge us to issue a tornado warning for a QLCS. So that's all the time I'll spend on that. As far as tornadoes go, another very helpful product is the multi-radar, multi-sensor, the MRMS that I mentioned before. It produces rotation tracks, which again, it stitches together multiple radars and comes up with like the best quality data for any point on the map. So taking the nearest radar, lowest level radar. In this case, putting together rotation tracks, which here zoomed in track for Southern Lycoming County, tracking a strongly rotating cell that moved through. And these are helpful in real time for identifying areas of rotation and tracking them and warning for them. They're also very helpful for determining where to go on a survey the next day after a storm comes through. Maybe we got a report, there's trees down in one area, but we're damaged that nobody has seen yet, and we'll use these tracks to guide us and tell us essentially where to go. because they calculate where that gate to gate or even just broader rotation, where it's strongest and what the strength was and how continuous it was and all that kind of stuff. Very helpful tool that we have in the toolkit. And then another multi-radar, multi-sensor product that I wanted to mention here is the maximum estimated size of hail. Also very, very helpful. We use it all the time for estimating essentially the size of hail to be expected in a storm. It's pretty good at letting us know when a storm can become severe with 1 inch hail. It'll start to light up with 1 inch hail estimates. And occasionally it can even pick up on size hailstones here in Pennsylvania that luckily often happen in the woods somewhere where they don't go damage people's cars and people's home roofs and all that, but occasionally they do. Become more impactful. We do see it occasionally, tennis ball size hail in the mesh, and we just don't have a way to confirm it unless we go out to the woods and ask some deer if they saw any hail. But it does happen in Pennsylvania. So another useful tool there, MRMS hail tracks. Okay, so that was all about severe applications. I want to go through quickly some of these clear air applications next. Poll question, just real quick, true or false, radar can only detect meteorological phenomena, i.e. storm, precipitation, etc. Actually, I think we could probably just skip this one. I think we've talked about it enough. You all know by now that this is false. It doesn't just detect meteorological phenomena. There's the bats and the birds and dust and other things that get picked up by the radar as well. I just wanted to show some examples of that. So this is just clear air. You might see this even on radar imagery tonight. I haven't looked at it, but it might look something similar to this. A combination of maybe some horizontal convective rolls, cells and stuff. It's kind of you can definitely see a pattern in the reflectivity, but there's actually no precipitation at all. This is just clear air. And the sky's probably blue this day. So what's it actually picking up? These are, again, bugs, bats, birds, dust. Could be the atmosphere has had some smoke in it the past few days from wildfires in Alberta. So it could be anything like that. And the way that you can tell that it's non-meteorological is if you look at those, then that's probably a biologic or non-meteorological particle. And also you can look at ZDR and things and birds and bats would have. Okay, in Texas, this is from the Austin San Antonio radar, probably a few years back now, 2018. But this is stuff that you can see on radar. Bats coming out of caves, birds roosting and their roosting patterns. They look pretty similar to this as well, but maybe you won't see as quite as many or as densely close together. Another couple of examples here. Actually, this one, let's see here. This slide is showing meteorological stuff here, and these higher reflectivity, number 1 and number 2, those are actually showers. You can see that the correlation coefficient values are higher. That's the red colors, but then in the middle, all this reflectivity is non-meteorological. Other things that you can see on radar include that's always kind of neat to look at. You can see this plume that has a common starting point here. That's where the fire, probably some precipitation forming.
Come on. Really? What, do you want to log off now? Thank you very much. Awesome. I'd not be surprised if this thing logged off. Oh, I think it did, yeah. Yep, I think it logged off. Yep, it logged off. 1 second. Technical difficulty. Apparently this thing lights. Now we get to miss some of it. In the meantime, listen to X40.
Sunny. Very warm. Highs in the mid-80s. Wednesday night, mostly clear. Lows in the upper 50s. Thursday, sunny, hot. Highs in the upper 80s. The 14-day outlook from Friday, June 2nd to Thursday, June 8th calls for near normal temperatures and near normal precipitation. Normal high temperatures across central Pennsylvania during this period range from the low 70s over the Allegheny Mountains to across the lower Susquehanna Valley. Normal lows range from
There you
the
go,
50s
y'all.
over the Alleghenies
Got the Wi-Fi
to the
back,
upper
but
50s
now
across the lower Susquehanna Valley. Here are the 7 p.m. conditions in the Harrisburg area.
I gotta go through email yet again, and then we can go to the webinar app.
The temperature was 68 degrees, the dew point 33, and the relative humidity
As far as what time you
27%.
saw something happen,
The wind
what
was
location, again, as specific as you can. What condition, and who are you? Let us know that you're a spotter. Here's a good example of what you might say. Hi, this is Mike. I'm one of your spotters calling to report hail. I'm located in Lancaster City. Might even give my intersection of the nearest roads near me. And we've got quarter-size hail falling right now, maybe larger. That would be a severe weather report. That would be good. Late reports are okay, but please try not to do that for tornadoes. That's something we want to know as soon as you can safely do so. Of course, get to safety first. If you need to run inside or run into the basement, do that first. Get yourself into a safe place, and then let us know that you're you've seen a tornado, so that we can get a warning out and protect some other people too. We really appreciate your videos and pictures, and those are good to send to us on social media or to our email address, ctp.stormreports@noaa.gov.
That's how I send things.
And then a little bit more guidance here, and this is again in the download and keep for yourself, but just some tips about reporting wind damage, hail, tornadoes, funnel clouds, and flooding. How to report. There's our phone numbers. We have the Facebook account, Twitter accounts, which are also good. And there's an email address there for photos and videos. But again, if you have a tornado sighting or even a funnel cloud or a rapidly rotating wall cloud, the phone is going to be the best way to get to us, and not our public lines, because the public lines get busy. They get filled up with callers when the weather is active. So you want to call us on the unlisted number directly. That goes directly through to us, and you'll be able to get a hold of one of the forecasters, and we can get a warning out. MPing is another application you can have on your phone to submit stuff, but not tornadoes. You can submit a report for a tornado, but don't, because we won't see it in time to get a warning out. And then one more thing I wanted to add. This was a recent request. There was a local municipality that wanted us to add this slide saying, please also report damage to your local municipality. The easiest way to do this is to call your municipal office. And the reason why this is important is at the county level, storm damages are tracked and the costs are added up, and that could be submitted to the state for assistance. So don't just let the Weather Service know, also let your municipality know about the damage. A little bit about CocoRoss here. If you're interested in the CocoRoss program, what they do is they have a rain gauge, and they report their rainfall amounts to us every day. If you're interested in joining that, you can let us know. And that is about it. So thank you all for sticking with us through the night. And if you have any other questions, please type them into the chat, and I'll answer them as they come in.
I don't have any questions, but there you
Looks
go,
like there's
guys.
a few questions there, so I'm just going to briefly read them here. Is there a few ways? There's actually a Weather Service archive of radar data that's available. It's hosted on the Amazon Web Servers. if you just if you do like a Google search of National Weather Radar Archive, you can probably find it pretty easily. The thing is, though, it's in like a radar weather file format. There's the Weather and Climate Toolkit, which is free from the Weather Service, which you can use to do that. But it's not the most user-friendly for everybody. Depends on your skill level at using meteorological data and software like that. So the simple answer is, yeah, it's out there, but it's a little bit challenging to look at sometimes. You download the class PDFs, you should be able to click on the handout section. So the GoToWebinar side panel has a handout section, and if you click on any of those blue names of PDF, that should allow it to click. But it might depend on your computer's security. Utilize drones for weather forecasts. We at the office don't have. We can't even use a drone for a storm survey. Although we're with local emergency management, if they have a drone, we can use the drone. We can use their imagery for a storm survey, which is very helpful for identifying storm damage and whether or not it was tornadic. But we ourselves don't have a drone. And as far as the Weather Service goes for like the information that they feed their models, there may be some drone information, especially sail drone kind of stuff that goes into weather. Maybe for some tropical cyclone cases too. There might be some drones involved with that. But I'm not an expert on that. That's above my looks like that's all the questions that have come in so far. What does the future of radar technology look like is another question we just got. There's a lot of different experimental radars out there. The phased array, which has been worked on for several years now, but as far as I know, there's still no plans. There's no concrete plans to switch to that at any point soon. A lot of the effort in the near term will be on radar applications, developing software, some AI software, and some other algorithms that can assist the forecaster in tracking storms, gauging is going to be near-term future of radar technology development. There's been a few questions about which apps we recommend, which software we recommend for looking at radar data, and unfortunately we can't, as a government entity, recommend any private sector software because we don't want to play favorites. We don't want to, advertise for one company over the other. So do your own research, try things out, and see what you like. Do you just print and sign the certificate, or is there any other certification requirements? There's going to be an email that comes out just to gather your information so we can add you to the spotter database if you're not already in there. Already a spotter, you probably don't have to worry about that. But other than that, there's going to be nothing else. Can the mountains and other terrain impact the radar? Yes, not too much in this area, other than, again, the windmills at the top of the mountains can be, showing as ground clutter. But there's no real beam blockage that I'm aware of in central Pennsylvania. However, there is in other states where the mountains are taller and the radar isn't situated at the highest elevation. I think maybe Vermont, and then some states out in the Rockies certainly have some beam blockage issues. Good questions. Are we ever bringing back Skywarn badges? Plans to at this point, but I can't rule it out. Something old becomes new again, so never seen that. All right. Looks like the pace of questions has slowed down. Are there any final questions, or?
So Mike, could you let me share my screen real quick?
Oh yeah, go ahead.
So hopefully you can see my screen now. And
We can.
So this is right now, and this is our radar.weather.gov. You can look at the local radar on here. So there's not, a whole lot going on. Clear air mode, really quiet. These are the windmills down here. But if we turn on velocity, zoom in to certain spots on some of the highways, you might notice the velocity here, which I looked earlier, and it's about 70 miles an hour. So does anyone know what that like? So the radar, if it, hits a road at just the right spot, this is I-99, it can actually pick up the flow of traffic. And then on I-80, it's getting it in a couple spots. And Buffalo radar, which if you don't know, I-90 runs pretty much right towards and away from the radar. And a lot of the time, you can kind of an interesting, thing that you can kind of pick up from the radar.
Radar technology is used, in many other things other than weather at this point. They're on most new vehicles. There's those little circles on the bumpers that have radar in them that can detect things behind you and how fast the car in front of you is moving. Of course, radar is also used by some police to see how fast your car is moving. And radar is used in baseball games to see how fast the pitch is. So there's many ways that radar can be used, and weather is just one of them. All right, I think that's it for the questions. So thank you all once more for taking the time to be with us for tonight, and wish you all well. Take care.
Take care, State College. So there you have it. That was the webinar as they signed off. So what you guys think? That's pretty cool, wasn't it? I'd say that was pretty cool. That was very cool. Now we can put the light back on because it's a bit like getting dark out. I'm going to put my shoebox back to where it was before. I had to use that for a stand. But that was it for State College. And there you have it. That pretty much was it for today's webinar. So, do hope you guys have enjoyed it. It's been really fun, actually, showing off the webinar that State College had intended for us to look at today. And I do have the MPEG app. What's this? Oh, okay, that's nothing. That's nothing I really need to worry about. State College was mentioning the MPEG app. I do have that. So, here we go. We're going to bring the tree back here, and we're also going to put the antennas back up on here for the radios here. So let me do that one second. And the seniors at my school are graduating, so I might actually go and watch that live stream if I can find that somewhere. I'm going to bring the Christmas tree over. But anyway, in the meantime, what did you guys think about the webinar? Hope the webinar was pretty cool for you guys, and I'd say it was pretty cool for me to showcase that. I thought it would be pretty cool to do. Okay, let's see if we can get this thing back in here. Alright, I won't stay on, but, Anyway, we're going to issue a test. Whoa, what the heck is going on? How the heck did I even do that if I didn't? Alright. I do have the MPEG app somewhere. But anyway, you didn't know much because you had dinner. That's okay. I mean, the replay is going to have the entire thing, so we're going to select a report. We're going to select just basically a test. So there it says test, submit the report. Or don't worry, we're just testing it, successfully submitted. We're just testing. So there you go. There was the National Weather Service. Oh, hey, Andes. There is the National Weather Service State College webinar. But anyway, I do really hope you guys have enjoyed. I'm going to sign off. and get prepared for tomorrow, because tomorrow is the last flippin' day of school for me. And I'm going to see if I can find my school graduation on here, because I'm actually wanting to watch the graduation. So I'm probably going to try to find my school's YouTube channel somewhere where I can watch it, because I do have the YouTube app. So here we go. I'm actually going to watch it. Let me see which channel is live. If it's there. See if I can search it up. Let's see. I don't see it here, so it doesn't look like it's here. Wonder how many flipping channels they have. They have like multiple. They have multiple. Let's see here. Oh, there's my stream. I don't see it. Uh-oh. Okay, I guess I can't watch it then, because I don't see it. Alright, hold on. Yeah, I don't see it, so... Yeah, I don't see it. So, I guess it's not being streamed. So, anyway, I do hope you guys have enjoyed the webinar. And, you wish Upton did a webinar? Well, I mean, it is pretty cool. It's pretty cool. But, anyway, yeah, I do hope you guys have enjoyed this. It's been very fun. But anyway, I'm just going to pretty much be checking up on notifications here. And yeah, so I do really hope you guys have enjoyed. And that'll be it for tonight. And I guess tomorrow, I might come on here around 11 o'clock in the morning, because that's when I get home from my last day of school. Last day of school. Last day of school's tomorrow. But anyway, yep, that's right. The last day of school's tomorrow. Finally, it's here. Finally, it's here. Then I'm able to go on my Maryland vacation. And then my UK vacation and all that stuff. So, I do hope you guys have enjoyed. And I might come on tomorrow at like around 11 o'clock-ish maybe for, I guess, the celebration of the last day of school. So, I do hope you guys have enjoyed this webinar stream. And I will talk to you all.